have shown something using mathematics, we did some theorem, we did another theorem, but what is physically, where is this physically volume charge and surface charge coming from? Well, to do that, go back to the dielectric, okay. So let us say this is a dielectric boundary that I have, and because of an applied external electric field, there are dipoles in this, okay. So now there are a lot of dipoles in this. I am showing only 5 or 10, but you have to assume that there is a lot of these dipoles, okay. So I have dipole here, I have a dipole here, sorry, this is not correct, okay. Then I have a dipole at the boundary, okay. Now it turns out that if I choose any volume here, okay, typically this volume would have dipoles. I am indicating the fact that there are these dipoles which are actually accounting for all the charges inside. In this volume there would essentially be a neutralization of the charges, okay. Each dipole will be paired by another dipole, and these charges would be all neutralized in the sense that they would be paired with something else. However, on the surface there would be this unpaired charges, and these are the equivalent surface charge polarization bound charges that we are going to get. So this is the surface charge distribution rho sp. So surface charges are actually created because of the insufficient cancellation of the charges inside the dielectric medium, okay. So inside the volume they have been neutralized, otherwise these charges are present on the surface, and these surface charges are the ones that are actually responsible for equivalent field distribution at some other point, okay. So this is the surface charge, and if there are volume charges they would actually be interior to the dielectric, okay. They will not be on the surface, they would all be interior to the dielectric. So rho sp, the surface charge density, is defined as P dot S, because we have to understand that the surface itself could be irregular in shape. So at every point on the surface I have to find out what is the surface normal, and then on that surface normal I have to find out what is the contribution of P on that surface, okay. So P is a density vector, okay, so it has certain orientation, remember that, and when you apply a potential there would be a component of that P along the surface normal, and that would form the surface charge distribution. Similarly, the volume charge distribution because of the polarization is minus gradient of P. So if at all you have a non-uniform dielectric, right, then this quantity will be not 0, okay. There would be certain volumes in which there is del prime dot P that is non-zero, and that would create the volume charge density, okay, of the volume, okay. So you could, as I said, absorb rho sp inside rho vp by defining the appropriate limits of the volume charge. Remember we did this, the most general distribution is the volume charge, then you could convert a volume charge distribution into a surface charge, surface becomes line, line becomes a point, right. An appropriate integration limits if you apply, you can convert a volume to surface, surface to line, line to a point charge. So you could accommodate this rho sp inside rho vp, and you can write V, the potential, as the volume charge integral of minus del prime dot P divided by 4 pi epsilon r integrated over the volume of the dielectric if I have absorbed rho sp into rho vp, okay. Now this is the potential, you could find out what is the electric field, right. So you could find out what is the electric field. Now we do not really want to find the electric field at this point, because this next argument tells us what is the relationship between the potential here and the potential due to the free charges, okay. So let us assume that there is some arbitrary charge distribution, okay. This arbitrary charge distribution is responsible for the external electric fields, right. So this is responsible for the external electric field and the potential at the field point. Now I have placed the dielectric here, and the dielectric is described by the equivalent volume charge density rho Vp, okay, and rho Vp is given by minus gradient prime dot P. So what would be the potential at this point? The potential will be because of the charge distribution, let us call this as rho F, F indicating free charges, okay. These are the charges which we have placed, and which are the charges which are actually responsible for external field and polarizing the dielectric. So I have free charges here and I have charges rho Vp. Therefore the potential at the field point would actually will be because of both free as well as the volume charges, right. So that would be rho F minus gradient dot P, this is the volume charge, divided by 4 pi epsilon 0 r dV prime, right. Again we are actually evaluating the fields at a very far away distance from the dielectric. Okay. Now if this is the field, right, if this is the field that I have, I could take it one step further and write down this as rho F plus rho Vp divided by 4 pi epsilon 0 r dV prime, right. If I define a rho total as rho F plus rho Vp, as far as the potential at this point P is concerned, which I am very far away from the dielectric, there is absolutely no difference between rho F and rho Vp. Therefore from the field point of view, that is from the point of view at point P where I am calculating the potential, both these charges add to the potential, right. Therefore Gauss's law has to be replaced from del dot D equal to rho F, which would be valid if there is no dielectric in between, to modify this Gauss's law to del dot D equals rho F plus rho Vp. But what is rho Vp? Rho Vp is del dot P minus del dot P. Okay. At this point it really does not matter whether I am looking at del prime dot P or del dot B. The del operation would essentially enclose on one big volume up here, right. See, this del operation that we are writing would actually be a volume around the field point that I am considering. Therefore it does not matter whether this is del prime. This del prime has to be done at the dielectric, whereas the del dot D that I am doing would be at the field point. Okay. So I can simply write this as del dot P and then pull this minus del dot P to the left hand side and I get D, sorry, I actually made a small mistake here. This is del dot D is equal to rho F is correct. However, the field that I have is actually because of, see, this del dot D equal to rho F actually becomes del dot epsilon 0 E, because I am assuming that outside of the dielectric this D field is actually epsilon 0 into E, correct. That is the field outside the dielectric. This would be equal to rho F plus rho Vp now, right. So with this I can move this rho Vp back into the left hand side because rho Vp is still minus del dot P, and if I do that I will get epsilon E plus P, okay, and this would be equal to the free charge density rho F, okay. So this epsilon 0 E plus P is given a name D, which is called as flux density, okay. So in terms of this flux density vector D, which is measured in coulombs per meter square, I now have full relation of D and rho, which is del dot D equals rho F, okay, where D itself is equal to epsilon 0 E plus P, okay. And you can clearly see that this D vector will be different in different materials. Why would they be different in different materials? Because the P vector would be different in different materials, right. Some materials will have a larger value of alpha E, some materials will have a larger value of alpha orientation, some will have a smaller value, some will depend on certain, if the dielectric itself is composed of many species of molecules, then there will be dependency on the position itself. Some clusters would be at a higher value of polarization, some clusters would have a lower value of polarization, right. So you could have inhomogeneous, you could also have anisotropic media in which this polarization vector depends on the direction of the applied field. So if I apply a field along say horizontal axis, then it would induce a certain polarization, and if I apply an electric field at a at an angle theta with respect to the horizontal, then that would induce a different kind of polarization. So you can actually have directional dependence, dependence on the space, and this one based on this polarization vector P. In fact, the polarization vector P need not even be dependent on, it need not be linearly proportional to electric field. It could in most cases when the electric field is very strong or very intense, then the polarization vector P becomes proportional to E square, E cube, e to the power 5 and so on. Okay, so such materials are called as nonlinear materials, and they are especially useful for nonlinear optics situations. Okay, we can do a lot of interesting stuff with nonlinear optics materials. However, the handling of these nonlinear optical materials, which are basically P depending on E square, E cube and so on, is slightly, well, slight is an exaggeration, it is actually quite difficult, and we will not be considering them over here. We will also not consider the inhomogeneous condition, that is, we will not consider the dielectric to be composed of different type of materials, so that epsilon itself is a function of spaced coordinates. Okay. So we will assume uniform dielectrics, for which we can characterize them by a simple number. Okay. We will also consider anisotropic materials very briefly, okay, but anisotropic materials will make their appearance quite after some time. Okay. We have just obtained a relationship between a new vector quantity d, which is flux density. Of course, we have already used flux density or vector d when we used Gauss's law to describe or to obtain the electric field when using Gauss's law. However, this is the formal definition of flux density d. Okay, you can think of d as defined in terms of polarization. Earlier I made a statement saying that chi e for free space is equal to 1, but that is not correct. Chi e for free space is equal to 0, but for any other dielectric it would be greater than 1. Okay. So chi e for free space is equal to 0. Sorry for my earlier mistake. Now we have seen that this vector p, in most cases it would be proportional to the electric field, the first power of the electric field E via the susceptibility parameter chi e, right. So I can introduce this p into the expression for d and write down d as epsilon 0 1 plus chi e electric field E. Now we have given a name for 1 plus chi e as the relative permittivity. Okay. So relative permittivity is 1 plus chi e stands for susceptibility, and for materials which are not free space, this value will be greater than 1, epsilon r will be greater than 1 for materials that are dielectrics and not free space. Okay. For free space, epsilon r is equal to 1, which again indicates that chi e will be equal to 0. For any other material, epsilon r is greater than 1. Okay. So in terms of that, I can write down d as epsilon 0 epsilon r electric field E. Sometimes this is shortened further and simply written as epsilon E. Okay. You have to note from the context that epsilon could be different in different materials, because the polarization vector P would be different in different materials. Some materials will have a smaller value of the polarization alpha, some materials will have a larger value of polarization, some materials would be at a different temperature, therefore their oriental polarization will be different, and for some materials it would be different value of oriental polarization, making the value of d to be different from electric field. Of course, this epsilon r is not a microscopic quantity, that is, this is not actually defined for a single atom or a single molecule or a single ion. This is actually a macroscopic quantity. You take a big piece of dielectric material, okay, and then you find out this susceptibility and then define this epsilon r, and when you are doing all this, you should remember that you are actually doing some sort of an averaging, because these materials are defined in terms of the polarization vector P, and remember what polarization is. Polarization is net dipole moment per unit volume. What was that unit volume there? That is the volume inside that of the dielectric. Okay. It would typically be a few angstroms wide, so that there are sufficient dipoles inside, okay, but it should not be too large. For example, if I am taking 1 meter by 1 meter dielectric slab surface, I should not choose the delta V, the unit volume to calculate the dipole, as 1 meter by 1 meter. It should be small, okay, such that on the level of where we are considering, we can consider the vector P as a continuous function. Okay. However, if you try to make it too small, then you are dealing with individual atom dipole polarization, right. In that case it would be very erratic, from atom to atom it would keep changing, and that is not a very good thing to handle for us. So you need to reduce the volume delta V such that on a level that we are considering, on the macroscopic level, P can be thought of as a continuous function of a vector, continuous function of the space. However, you would not consider delta V to be so small that you are looking at irregularities on the atomic scale, unless that is your interest in the problem. Okay. Similarly, epsilon r can also be considered as a function of space. In addition to epsilon r being function of space, it could also be a function of direction. For example, there are certain materials which would be polarized in one direction with a certain value, and if you apply an electric field in a different direction, then they would be polarized with a different value. Okay. So this directional dependence can also be considered macroscopically and attributed to the susceptibility chi e or the permittivity epsilon r, or its shortened version epsilon. So we say that epsilon, which varies with respect to space or the spatial coordinates, as inhomogeneous dielectric. If epsilon is a function of the angle of the applied electric field, that is direction of the applied electric field, then such materials are called as anisotropic materials. And in most cases, when the electric field inside the dielectric medium becomes very strong, then P will start to become function of second power of electric field, third power of electric field, and so on. Such materials in which the polarization vector P depends on not on the first power but on the higher powers of electric field are called as nonlinear materials, and nonlinear materials are particularly useful for nonlinear optical applications. Okay, you can actually take two wavelengths and create a new wavelength, you can take one wavelength and create half a wavelength. Okay, you can do all sort of things when you have nonlinear materials. In this course we will not be looking at nonlinear materials, we will be looking at linear anisotropic materials. Anisotropy of course makes its entrance quite late in the program or in the course. Okay. Alright, so we have D is equal to epsilon times E. Now let us ask this following question. Suppose I have a dielectric slab, okay, let us consider this to be a Teflon slab, okay, and this Teflon is given by a susceptibility chi e of 1.1, okay, at some temperature this chi e is 1.1. What can we say about the fields inside and outside? Let us assume that outside the fields are all uniform, okay. So the electric field outside, let us call this as E out, is given by U hat and has a constant intensity E0 measured of course in volt per meter. U hat simply indicates upward directed electric field, okay. I did not want to specify this as X or Y, so it is upward directed electric field. Outside of the Teflon slab, you know, on the other side again I have the electric field outside of the slab as upward directed uniform electric field of magnitude E0 volt per meter. Now what can I say about the fields inside the dielectric? Well, all I can say about the fields inside the dielectric is, if E in stands for the field inside the dielectric, then P in, the polarization vector or the dipole moment density, right, that would be equal to epsilon 0 chi e times electric field in, which is 1.1 times epsilon 0 inside electric field E in. What would be D in? The D vector would be 1 plus chi e times epsilon 0 E in. 1 plus chi e is 2.1. So this fellow will be 2.1 epsilon 0 E in, right, with appropriate measurement units. Now if you ask, well, you were given what is the electric field outside the material, and what stopped you from finding the electric field inside the material? The answer is, I know how electric field inside is related to polarization and D vectors. I know how the electric field is varying outside, but I do not know how to relate these two things, right. I do not know how to relate electric field outside to electric field inside, and to obtain that relationship we need to understand boundary conditions, okay.